Hey Ruth, hey Kaylee. Can y'all hear me okay?
Yeah, I can.
Yeah, I can hear you too.
Okay, cool. Hey Whitney. Hey Ruth.
Yes,
You're on your iPad?
I am on my computer, but I can also join on my iPad if you
No,
need
no,
be.
that's fine. Can you, from your computer, can you see if you can share the homework assignment worksheet in the chat? Maybe I can get it. Never mind. I'll get it and then I'll share my screen. Hang on. I'm gonna go get
Okay,
that homework
good.
assignment that was not very good from lots of people.
Okay, because I did not want to share my grade with that.
I didn't mean to share your home. I meant that just the worksheet. I wouldn't make you share your grade.
Oh, yeah.
Okay. I need to open that. No, thank y'all for being flexible. Sorry about this. I planned to come back, but then I was thinking about her, um, my daughter with a fever, having to like ride to campus with me for 30 minutes and then go sit in the carpool line with my husband for an hour. And it just didn't seem right. So we're just gonna make the most of this. Hopefully it'll be fine.
Hey, there's like three people in the classroom. Is there a way that we could use the projector and do
Yeah,
class that way?
yeah. Um, do you have uh, you're on your computer, Ruth,
Yes, I am.
and you're in the classroom right now?
Yes, I have Charlotte and
Do you have an
Logan.
HDMI port or a VGA port on your laptop?
I'm not sure. I might.
If you do, walk up to the podium and plug your computer into the cords that are hanging off the top. There's an HDMI one there or a VGA one. Um, you can do whichever. And then the remote, talk me through this so I'm not just talking at you.
I don't have the capabilities. I think Logan might have it, so Logan might be able to. Yeah.
HDMI or VGA, it doesn't matter. One of the two is fine.
Okay.
And if you just plug the computer in, Ruth, is the remote around visible to you?
Yes, I see the remote.
Okay, turn the projector on. Logan, when you plug your computer in, there is a smaller little, it's the sound cord that you would
He
plug into
can't
like,
hear you. He can't
oh,
hear you. Hold on. Okay, he should be able to hear you now.
there is once you plug into VGA or HDMI, there's also in that like collection of cords, there's a smaller cord that is like a headphone jack cord. If you have a headphone jack on your computer, you would want to plug it in there. and then the sound can come through the room. If not, it would just be the sound on your iPad. I mean, on the computer, which might be fine if there's only 3 of you in the room, or 4 of you, or whatever.
4 of them. Okay, so now all you have. Oh, it's Apple.
Just hit the source on the remote.
I can do it through Apple. Hold on.
No, listen to me. Hit the source on the remote. I don't want you to do it through your iPad because I want you to be able to take notes.
No, I'm talking about my computer.
Oh, your Mac?
AirPlay. Yeah.
Yeah,
Hold
but
on.
then we would not have sound unless you have a headphone jack on your phone.
Are you connected?
Yeah.
Okay.
Okay, so did he get the sound cord plugged in too?
Yes.
Okay, so up on the wall right behind the podium is a little twisty knob for the sound. You're going to want to turn that up to see if my voice comes through the room.
Install the which one? This
Well, no. Got it. You said hit the source button.
To switch to the HDMI or VGA to get it off the Apple TV, yes.
What is it? HDMI.
It'll just go. It'll just go. Just hit it one time and it'll go.
Oh, got it.
And then the volume knob on the back wall, you got that?
We got that.
Okay.
No,
You can hear me. You can see everything.
No, he doesn't have Zoom installed on his laptop.
it's quick.
You
I'm
should
probably
you should be able to do it through the website. It shouldn't matter.
join through your browser.
It's almost done.
It's almost done. When he gets it installed, I'm gonna get out.
Of Zoom.
Yes.
Okay, that's fine.
Using cameras.
I don't think we have to.
You don't need to use the camera, but I would like for you to turn the mic on in the classroom so that I can, if y'all are talking to me, I can hear you and somebody doesn't have to get up to turn the mic on.
Answer question.
Okay, I see Logan in there.
Okay. I am leaving.
All right, sounds good, Ruth.
Can you hear me?
I can hear you. Perfect. I'm gonna share my screen and y'all let me know if you can see everything and if you can hear me and stuff.
Hello?
Can you not hear me?
Recording.
Can
you hear us?
I can hear y'all.
Oh no, she is.
She is.
I can hear y'all. Can you hear me?
I shouldn't have left until you got.
Not hearing.
Turn up volume. Turn up.
Yep. Turn up the
Can you
volume
hear
and
us?
then
Oh, there we go.
But it's not going through the room.
It's not going through the room.
is the
That's
little black headphone jack cord plugged in?
Oh, do you mean the other? Hold on. She might mean this one.
It's little tiny, like a little single.
About this one.
Can you hear us?
I have been able to hear y'all. It's about you hearing me.
Yeah.
Not. That's not it. That's not connected to your computer. Put screen.
There's a real skinny cord, a really skinny cord that would go in a headphone jack on your laptop.
Yeah, I've got it. It just didn't. Unless I have
And
to
then
switch the
the
audio over
sound,
to.
the sound in the room, you might have to switch the audio. In Zoom, you do probably have to switch the audio over.
Not here, in Zoom.
It's fine if y'all can hear me from his laptop, just do that and then we can get started.
Now I'm looking for it.
Not good. No.
Here, let me try. I might just have to switch the audio from this.
Speaker audio, maybe.
It's Realtek, Intel. Display audio. Did that work?
Can you hear me now?
Nope. Sorry.
What about that one?
Can you hear me now?
Oh, we can hear you through my
Yeah,
laptop. I'm
I
trying to
know.
figure out.
I'm just trying to continue talking in case it does switch into the room.
Yeah.
Oh, that's gonna not.
Yeah.
Ooh.
I don't see any. Oh, that's her screen. I saw the little mic thing, and I was like,
Oh,
It's at the bottom. It might be at
is
the
that
bottom.
the record chat participants?
No, on the other side. The mic. You see where it says
This?
mic, and yeah.
Oh, here we go. Select the speaker.
Yeah, there we go.
can you
that
hear
it?
me now?
Yeah.
Woo! Got it.
All right, good job, everybody. Okay, I wanted to walk through. Are y'all ready for me to go?
Yeah.
Okay. I wanted to walk through a couple of these proofs that were iffy from y'all, from the ones that I have graded. So Charlotte, if you have yours done, email it to me now so that you will not get credit for this, since other people didn't. And I know you're working on it. So, but anyway, the things that were the biggest issues on this homework were these two questions, getting the contrapositive right on this question. This left a lot to be desired. So did this one. So did this one. So I want to talk through some of those. These are, in my opinion, this is pretty important for us to get nailed down. And so and we'll do this first. We'll do a little bit more set stuff. I was telling Ruth earlier that some of the set stuff y'all want me to get through because you want me to put this on the test because it's easier than y'all writing more proofs like this. So we're gonna just go through a couple of these and then do some more set stuff, and then we'll have time for me to answer any questions that you guys have as you prep for Thursday. Now, remember, you do have a note card for Thursday. If I was in your shoes, I would put like a generic proof by contrapositive, a generic proof that something is irrational. You know, you've done a lot of those in this on this homework assignment. So stuff like that, I would, if you can fit it on your note card. Definitions, if you're concerned about remembering definitions of like divides and rational, and what else do we have on this test? I don't know, but things like that. But let me not waste any more time. Let me go through the way that you would do the contrapositive for like 2 and 3. On number 4, the biggest issue was the statement of the contrapositive for y'all. The negation of this statement, which is an or statement, becomes an and statement. A lot of you did not do that. You kept it as an or statement. So this would be that x is odd and y is even. If those things are true, then x squared times y plus 3 is odd. Now, y'all did prove that, but you didn't have the assumption right. So anyway, okay, so that was that. 2 and 3 were a little bit different. I want to talk you through those two proofs. Some of you got creative and they were good, but and then we'll talk through some of the other ones. But on number 2, I'm just going to do sort of scratch work stuff for this one, but the contrapositive here would be that if x is strictly less than 0, then x to the 5th minus 4x to the 4th is strictly less than 0. So x is a real number. That's what we're going to start with. This is a proof-ish. Let x be a real number and assume x is less than 0. I would say something like notice x to the 5th minus 4x to the 4th. Now this is the factoring like trick, I guess, here, that this is x to the 4th times x minus 4. We know x to the fourth is always positive for all real numbers, or always non-negative for all real numbers, but for all x less than 0, it's certainly positive because it's to an even power. And x minus 4 is less than 0 for all x less than 0. Thus, their product, so x to the fourth times x minus 4, is less than 0 for all x less than 0. So by contraposition, if x to the fifth minus 4x to the fourth is greater than or equal to 0, then x is greater than or equal to 0. There's sort of a like trick there with factoring. Actually, that's not a proof-ish. That's a really good proof. So the trick there is with the factoring, and I call it a trick. It's not really a trick. It's a method. But anyway, the same kind of thing you would use on number 3. I have no good way to read if y'all are okay with me scrolling around or not, but I assume somebody will panic and I will hear it maybe. Number 3 is a similar kind of thing. The contrapositive here is that if x is less than or equal to -1, then x cubed minus x is less than or equal to 0 for all x and r. Well, I guess not for all x and r, but x is r. Okay. Boy, that element leaves. There we go. Okay. Here it would be your proof of this one. We're gonna let x less than or equal to -1 be a real number, or let x be a real number that is less than or equal to -1. Notice this is another factoring thing. X cubed minus x is equal to x times x squared minus 1, which is equal to x times x plus 1 times x minus 1. Now, x is less than or equal to -1. X plus 1 is less than or equal to 0. And x minus 1 is less than or equal to -2 when x is less than or equal to -1. Okay, so breaking up that into that product. So x is less than -1 for this piece when you plug in -1, which is the like biggest it can be, then that would be no bigger than 0. And then this thing can be no bigger than -2 because x is smaller than -1 or equal to it. So that each of those things, when you multiply them together, you will have a thing that is less than or equal to 0. Right? Now I have talked myself out of this argument.
Wait, how would x plus 1 be less than 0?
Because x plus 1 would be less than or equal to -1 plus 1, which is 0. Because x is less than or equal to -1. And then x minus 1 would be less than or equal to -1 minus 1, which is -2. And x is less than or equal to -1. But those multiplied together, that's a negative times a negative times 0. Oh, no, because if this is 0, the product is 0, and if it's not 0, then the product would be negative. We good, because 3 negatives make a negative, or 2 negatives and a 0 make a 0, and either one is good. x times x plus 1 times x minus 1 is less than or equal to 0 whenever x is less than or equal to -1. So by contraposition, if x cubed minus x is greater than 0, then x is greater than -1. It's a good idea to either at the beginning or the end of your proof state the thing you're trying to prove. So we will prove, the other option would be to say like here, we will prove that x cubed minus x is greater if this, then this, we will prove this using contraposition. So let x equal -1, x be less than or equal to -1. So say at the beginning, we will prove by contrapositive this thing. Let x be less than or equal to -1, or do it like this and then say at the end, by contraposition, we have shown that the original thing is true, right? So the point of doing the proof by contrapositive is that you are actually showing something else to be true. And so stating that thing at some point is a good idea. It's good proof structure, shall I say. Does anybody in the room or not in the room have questions about that? Okay, I'll take your silence as confirmation that you're with me. This is a pretty interesting proof. Do y'all want to look at this one?
I thought we did something like it. That's what I was basing my answer off of.
We actually did. We in this one you assume that it is equal to 0, and you get that like 2 divides a or something, and then use that and you get an even equal to an odd eventually, like 2 equals 1 plus 2b or something. 2k equals 1 plus 2b. So you like do proof, you get 2k equals 1 plus 2b. This is an even times an even equal to an odd, which is a bad thing. That's what happens in that one. On these guys, you're basically just chasing definitions. So a lot of you like let x be a rational number, but you didn't actually let x like equal an integer over an integer. So just like go back and do that. I did want to talk about this one and this one. So let's do those kind of quickly. This one is similar to what we have done. And I try to warn you guys about this in class, that you're going to get to a point where you have this thing that's not prime that you're saying divides, b squared or whatever. And you have to be careful about how you say this. So we're going to do our proof. We're going to suppose not. Suppose the cubed root of 6 is rational. Then the cubed root of 6 equals a over b for some integers a and b with b not equal to 0. And then you would say something like, notice you're going to cube both sides here instead of squaring them because it's a cubed root. So to get that, by itself, you're looking at 6 equals a cubed over b cubed. So 6b, well, my 6 and my b's look a lot alike. 6b cubed equals a cubed. And then you need to do this thing, and I don't know, I'm going to do it with 3 because why not? Factoring that out, we're looking at this, and you would say something like, since 2b cubed is an integer, 3 divides a cubed. Since 3 is prime, since 3 is prime, 3 divides a. Thus, a equals 3k for some integer k. Oh my gosh, sorry. Then notice the transitional words that are happening. 3 times 2b cubed equals 3k cubed. I'm trying to keep my palm off my iPad now because it kept doing that paste image thing. It's kind of annoying. But now my handwriting sucks, so we're just going to go back to it. 3 cubed is 27. And then dividing by 3. 3 times 3 is 9 times 3 is 27. Yeah, okay. Dividing by 3, I have 2b cubed equals 9k cubed. I'm going to write this as 3 times 3k cubed. And I'm going to say this. So since 3k cubed is an integer, and 3 does not divide 2, it must be that 3 divides b cubed. And then since 3 is prime, 3 divides b. Now we have, oh crap, always do this, y'all. Go back to put this here. We assume GCD of A and B, this one. Okay, assuming GCD of A and B is 1, let's just pretend that I had that there all along. Now we have 3 divides A, oh Lord, 3 divides A and 3 divides B, which contradicts our assumption that the GCD of A and B is 1. It must be that the cubed root of 6 is irrational. All right. Is that making more sense now? Oh, okay. Yes or no? People in the room talk.
Yes.
I have a
Yeah.
question.
Yes, go ahead.
Do we have to like say like by contradiction or something here or no?
So I think that this is your sort of indicator that you are doing it by contradiction.
Mm-hmm. Okay.
So I think that's your, and then like saying this again later, like, yeah, I'm still doing a contradiction proof, and then state the original thing.
Okay. Okay. Thank you.
Yep. Okay, any other questions about number 9 on that homework assignment?
Mm-mm.
All right, the last one on this homework that I want to walk through is number 10. All right, so on this one, this is a fun proof, and I think that this is actually pretty useful, but it is different than what we have seen. Most of the time, when I give y'all homework assignments, I have like, I have forgotten what the questions are, right? And so until somebody asks me a question about something, like I don't remember it. And now, like after I looked at your homeworks, these couple of questions, these guys that we're going through now are questions that in the past I have worked through with my students in office hours and stuff, or in class they've asked me like the day before it's due and stuff. Y'all can do that, you know, you don't have to turn stuff in that you're uncomfortable with. You can ask me questions and I will answer them. I would love to help you. So, you know, in the future, don't be afraid to ask. And when I give you a day of class between like when I tell you it's going to be due and when it's due, that's so that you can ask me questions in class. So, you know, take advantage of that. Look at the stuff when I assign it or when I give you a due date, because once I'm giving you a due date, it's most of the time that we've covered the material at that point. So look through the things and, you know, so you can figure out what you have questions about and ask me about it before it's due. Okay, so we would do on this one, suppose not again. Suppose instead, so suppose that the nth root of p for p, a prime number for prime p, is rational. Then the nth root of p is equal to a over b for some integers. I'm not going to forget this time. Integers a and b with b not equal to 0. Assume the GCD of a and b is 1. Now, nth root of p equals a over b means that p is a to the n over b to the n. So p b to the n equals a to the n. So since b to the n is an integer, we have p divides a to the n. And since p is prime, this only works for the primes. That's, sort of the point. This is Euclid's lemma. So since p is prime, p divides a. Thus, a equals p times k for some integer k. Now, p b to the n equals p k to the n. Writing p's and b's next to each other is weird. Okay, so you're looking at this. You're going to divide both sides. The n is just the number of copies of p sitting there. So you can, get one out of there, and it's just now that there are n minus one of them. And the way that I would do this, just to make it like explicitly clear, is to write it this way, where you pull another one out, and say something like, since p to the n minus 2 k to the n is an integer, p divides b to the n, and since p is prime, p divides b. We have p divides a and p divides b contradicting our assumption that the GCD of a and b is 1. It must be that the nth root of p is irrational. All right, questions about that one at all? I don't know how to get this thing out of the way. But that's not helpful. Okay, do you have questions? Oh, no. Okay. I do think that you should be prepared to, prove by contradiction that something is irrational. And obviously you should be able to write a contrapositive and to prove something using contrapositive. It would not be a bad idea if I was in your shoes to go back and like review how you negate like pieces. I mean, this is De Morgan's law. This one, negating that piece is De Morgan's law. Distribute the negation and flip the what is that called? Whatever. Flip it from an and to an or an or to an and when you distribute that negation. Okay. Any other questions from that homework assignment that you guys want to talk about? that's a no. The so your homework that's due on Thursday, you're just going to do 6.1. It's just the 5 problems from 6.1. I think it's 5.
So we're still turning it in, even though it's 6.1 and 6.2, that's on the, like, homework 7 or whatever.
Right. I'm going to have you turn in just half of it, just the 6.1 half on Thursday. Just those 5 problems.
Okay.
For the WebAssign homework, do
Yeah.
we do 6.2 or is that going to be
No.
due next
No,
week?
I'll move it.
Okay.
I'm making a note of that right now. That's really hard for me to do from my iPad, but I will, because I have to like drag stuff and it doesn't respond to well. I will try. I almost spilled my coffee and dropped my iPad. I'm making a note somewhere, but I don't have any paper. Whitney, your job is to email me to request, no, not don't request an extension through WebAssign. Just email me and remind me to change the WebAssign dates.
Okay, I'll do that.
Okay. All right, so we are going to go through right now and do a little bit more from our note packet. That's not where we need to be. Okay, so this is where we were. Yes, no,
We didn't get to the Venn diagrams.
right. We haven't, that we finished on page 21, right?
Yeah, that's
We
right.
talked
Yeah.
about subsets. Subset, it means that every, like if A is a subset of B, then every element in this set is also in this one. And elements, we talked about 2. These are just the like members of the set. So like 2 is an integer, but 1/2 is not an element of the integers. Sorry, I just hit my headphones. Don't know if I hit my microphone too. Sorry. Okay, so we did all this stuff. We talked through all of this. So most of the heavier proofs, we'll do some like easier proofs in 6.1, but the heavier proofs are 6.2. That starts on page 27. Yeah, so this is going to be moved to test 3. So we'll stop on page 26 today. Okay, let's go back up here and we are going to talk through some of this and then we'll just see where we are. Again, when you are doing subset proofs, and we're going to have some simpler ones, but when you're doing subset proofs, you're going to pick an arbitrary element in this set and then show that it has to be in this one. How would you prove instead that like A is not a subset of B? If to be a subset, right, for A to be a subset of B, anything in A has to be in B. So to prove something is not a subset, you want to find an element in A that isn't in B, that isn't contained in B. And then that would, show you that not every element in A is an element in B, which shows it's not a subset. Okay. Here we go. Here's our first subset proof. This one, like I said, is, pretty easy, but we're going to be great. I'm going to do just like a scratch work and maybe I'm not sure. Let's see what happens. So we are going to let A, B, and C be sets. Assume, right, so such that this thing, right, this is our if part. Oops, sorry, I shouldn't have stopped there with the word assume. Assume that A is a subset of B and B is a subset of C. And this is what we want to show. So we get for free that A is a subset of B and that B is a subset of C. This is a transitive property for subsets, which is fine. We want to show that A is a subset of C. So what we're going to do, because this is our goal, we're going to pick an arbitrary element over here. So pick little a and a. And I told you, Charlotte, we were going to do this thing where we label the sets with capital letters and the elements in them will have that same letter but small. And this is so you know where they're from. So we're going to pick little a and big A. And we want to show that little a is actually an element in big C. So how are we going to do that? Well, we actually know that A is a subset of B. So little a is an element in B. And because B is a subset of C, that means little a is actually in C. So we did it there. This is one of those times, in my opinion, where it's like you over explain something that isn't that hard and it makes it sound harder. But let's write it out and see how we are doing. So we are going to let A be an element in A. Since A is a subset of B, we have that little a is also in B. Now, since B is a subset of C, little a is in C.
We're allowed to use the symbols in the room?
Yeah.
We have to, right?
No, because you could write out like is an element of, but when you're doing the set notation stuff, like it's fair game. I know that is bothersome because I've been pretty adamant about you not doing it, but when you're doing a whole bunch of set proof stuff, then I mean, it's going to get harder to understand and harder to like comprehend if you use a whole bunch of words that you don't need. Okay. I'm trying to word this the best way possible. I don't know, whatever. Thus, A is a subset of B. But C, my bad. That's A is a subset of C. Since every element in A is an element in C. When A is a subset of B and B is a subset of C. Okay. Like I said, that's not a very like complicated set proof. I think that's pretty straightforward. So because you can just sort of like imagine that, right? If you were drawing a Venn diagram, which we haven't done yet, but if you were drawing a Venn diagram, you have A is completely contained in B, and B is completely contained in C, then it makes a whole lot of sense that A is contained in C also, right? So there's like not a way to draw that picture any other way. So okay. This one is fun too. I like this proof that for every set, and we said this the other day in class, that the empty set is a subset of every set, and the full set itself is also a subset of every set. So we're going to actually prove that. So I don't know if this is actually a cool proof or not. Okay, so we're going to let S be a set. Since there are no elements in the empty set. Ooh, don't put something in the empty set. That's the empty set, or, for any, so we're going to write it like this. Since there are no elements in there, they are all contained in S. So the empty set is a subset of S. Yeah, you're going to like this one. Now we're proving this part, that S is a subset of S. Let S be in S. Then S is in S. So S is a subset of S. Ta-da! So nothing is contained in the something, and the something contains its own something. Always.
Interesting. Can you go back up so I can take a picture real quick?
Yeah.
There we go.
Of what this?
Yes.
There's this sometimes people will. Somebody asked in class, Charlotte, I think it was you, about this symbol looking like a less than or less than or equal to thing. So there is this idea where you're looking at proper and improper subsets. And so what that means is the full set itself is an improper subset. Because it actually equals itself, but everything else, every other subset is a proper subset. It's properly contained in, it's not equal to. And I don't, we don't make this distinction. There's no reason to for what we are doing with it. But so this notation could be proper or improper. But if you knew it was a proper subset, you would use this because it is a stricter thing. Like think about this as a less than or equal to, and this as just a less than. So that means that there is something else. There is at least one element not in the subset, but in the set. So that's like this, you would never use this thing without the bar for S being a subset of itself because it is an improper subset because it's actually equal to. Okay. Now, like I said, we're not going to do anything with that distinction, but you might hear that down the line somewhere, and I don't want to have let you down. So, okay. Like we just said that the two sets are equal, like S is equal to itself, and that is happening if they have the same elements. But this is when A is a subset of B and B is a subset of A. You think about this as like an if and only if kind of a thing. So every element in A, well, is contained in B, and every element in B is contained in A. Now, we'll talk about this, the proof for that in just a minute. Okay, how you would do a proof for those. So the question is, are these sets equal? So we're looking at number one, we have the set 1, 1, 3, 3, 3, 5, 5, and then the set 1, 3, 5. Are these sets equal? And the answer is yeah. They have the same elements. The elements are 1, 3, and 5. When you're listing a set, you don't need to list the elements more than one time. A tree, if you're counting an apple tree, you just need to count that apple tree one time, not multiple times. They have the same elements. Every element over here is over here. Sorry, it's not a pin. Every element over here is over here, and every element over here is also over here. So those sets are equal. The question would be this one now, and you can look at these sets and tell that they're not. This is this. Is this equal this? No, it doesn't. So you can also think about this as like those empty braces with the empty braces that contain another set of empty braces. Like, no, those are not equal. So
Why aren't they equal? I mean, they're both empty sets.
no, they're not. This is an empty set. This is the set containing the empty set. So this has
Oh.
one this set has one thing in it, specifically the empty set, and this set has no things in it.
Okay.
I mean, it's a weird thing, which is why we're talking about it. So, but yeah, that's the difference. And I think the visualization, like they don't look the same, do they? So they're not the same.
No.
I'm trying to find out the I don't have cardinality written on here anywhere that I can see, but it's here, so perhaps we should talk about it. We'll talk
Which-
about it when we get there. But when we get to the cardinality, remind me to come back and talk about this one. Okay, so question number 4, how would you, is somebody trying to ask me a question? I'm so sorry, I'm talking over you.
No, I was just gonna ask you about if it was the product one, so I looked at the definition, one of the definitions, and it was like A times B or something.
Yeah, that's the Cartesian product. We're gonna move that to test 3. That's the start of the test 3 material.
Okay,
Hopefully that's not in 6.1. Whatever. If you get to a Cartesian product thing, we're not gonna do that yet, so let me know. All right. Where are we? Question number 4. How would you write the definition of A equals B in logical symbols? This would be that for all X, I told you it's like an if and only if statement. X is in A, if and only if X is in B. Okay, so in general, to do this proof, you would do this 2 ways. You would do 2 parts. You would prove first that that A is a subset of B, and prove second that B is a subset of A. And if A is a subset of B and B is a subset of A, it must be that they're equal. So you would, for all X in A, that X is also in B. Here, for all X in B, you would show that that X is also in A. Okay, so an equal to proof is just 2 subset proofs going each way. Okay, and that's sort of what this says here. This is an example of biconditional proof, which can be organized in 2 different ways, showing both P implies Q and Q implies P, or a series of if and only if statements. I am really, really cautious about doing, I don't do this like hardly ever because I get scared sometimes. I have anxiety, that's a real thing, but I get concerned that I'm going to misuse an if and only if and break everything. So I will pretty much always do a 2-parter proof where I prove it one way and then prove it the other way. And a lot of times it's just writing the steps down backwards, but that's okay. I feel fine about that. So anyway, that's that. Let me see. I think that we can do this proof. It's not the easiest proof to start with, but you know, then our lives get a whole lot easier after that for today. How about we'll come back to this and we'll do some easier stuff and then we'll come back to this proof. I need to make sure I give myself time to do that, but we'll come back. That's not gonna work. Come back to that. Oh, look, I got ahead of myself. A proper subset if A is contained in B, but A doesn't equal B. Good. Okay, now you can imagine that all of these, any subset order for these is going to be proper subsets because none of these things are equal to the other ones. That's why they have different letters. So the natural numbers would be your like smallest set. Those are contained in the integers, and those are contained in the rationals, and then those are contained in the reals. Mine look like less than signs too. So that's sort of the hierarchy of those. The whole numbers would be in between here, I guess. Anyway. Okay. So set operations. We're doing Venn diagrams. Excuse me. The universal set U is represented by a rectangle here. This is U. The sets being considered are represented by circles. Venn diagrams are used to visualize the relationships between sets. Okay, so A is subset of B with the universal set U looks like this. A is contained, little a big A, sorry, is contained in B, then they're both sitting inside the universal set U. Okay. Unions and intersections. So a union of sets A and B, denoted A union B, is a set that contains elements that are in either one of the sets or both. So your Venn diagram for this is all of these guys. The union is it's like I think about this as in A or in B or in both. So this is a set of all X such that X is in A or X is in B. It is no coincidence, y'all, that the union and the or symbol in logic look very much the same, because they are. We're just doing set theory now, not logic, but the idea is the same. De Morgan's law also applies here too. So we have shaded the region. So if A is the set 1, 2, and B is the set 1, 3, 4, what is A union B? It would be all those things that we can see, 1, 2, 3, and 4. Anything that's in A with anything that's in B. Don't write some things down twice. The things that you would write down twice are the things you're going to write down for the intersection. Do you have any questions about the union right now? Okay. The intersection, y'all, is where the sets overlap. So this is probably something that you know, but the intersection is actually that is where the two sets intersect. So the elements in there would be the things that are in both. So the X is in A and X is in B. So that region again is this little guy where they overlap in the Venn diagram. If you have the set A, that's 1, 2, and the set B, that's 1, 3, 4, A intersect B, is anything that you see in common, you're going to write it down. So just the element 1 appears in both sets. So that's the only thing that would be in that middle portion of the Venn diagram. Here's definition. The two sets, they're disjoint if their intersection is empty. That looks like what you would imagine. It looks like this A intersect B is empty and they don't have any overlap. Those are disjoint because they are not joined. Okay, they have no elements in common. Set difference. Now this is fun. I think if you read this as, this is how I read it, as a toss B. And this is a different notation for that too. This sort of, oh, is this a forward slash or slash? I don't know. This slash. This is the set of elements that are in A but are not also in B. And when you think about this on the Venn diagram, it's easier to see. It's the stuff that's just in A. You look at A, everything in A, and you toss this region of B that overlaps with it. So it's the stuff where X is in A and X is not in B. So we have the set A is 1, 2, 5, 6, and the set B is 1, 2, 3, 4. So A toss B is going to be the stuff in A that is not in B. So the B has the 1, 2, those overlap. So A toss B is just going to be 5, 6. I don't care what else is in B when I'm doing the A toss B stuff. The only part of B that I care about is this part here that I need to toss away. I don't care what else is going on in the rest of B. I care about where it overlaps with A and getting rid of those numbers. Okay. Number 11, the complement here. So the complement of a set is the stuff that's not that set. So this is a bar or a C, or sometimes that's on a pin, sometimes a with a prime, like a tick. This is the set of elements that are not in A. So a complement is everything else. So A complement on your Venn diagram is everything that isn't in your bubble A. So if our universal set here is 0 through 9 and A is 1, 3, 4, A complement is going to be everything that's not in A that is in our universal set U. So 0, 1 is gone. 3 and 4 are gone. So 2, 3, 4, 5, 6, 7, 8, 9. You can think about this as U toss A if you wish. That's a different way to do it too. Take the stuff in U and remove the stuff that's in A. So you would get rid of 1, you would get rid of 3, and you would get rid of 4, and you would be left with 0, 2, 5, 6, 7, 8, 9. Okay, do y'all have any questions about those things? Like I said, you want me to give you a question where it's like, do this to a bunch of things, right? Here are 3 sets, do some set operations, right? Like this, a problem like this. This would be fun, right? If A is 1, 2, 3, 4, 5, and B is 0, 3, 6, find the following set. So A union B, remember this is anything in A or in B. So I'm going to write down everything in A and then the stuff in B and not writing down things twice. So I didn't need to write down that 3 twice. But the fact that I would have had to write down that 3 twice means that it is in the intersection. And it is the only thing in the intersection. All right, A toss B. I'm going to take A and I'm going to remove anything that B shares. So I'm going to remove that 3 that they share. So A toss B is the set 1, 2, 4, 5. These are all sets, y'all. These answers are all sets themselves. So make sure you use your curly braces around your answers. Then B toss A, I'm going to take B and I'm going to remove anything that A has. So I'm going to remove that 3. So B toss A is just 0, 6. Okay, questions about that?
No.
Okay.
Well, hold on. Sorry.
You're fine.
So the union is the when you smash it together, right? Or put it together.
Yep.
And the upside down, you like
Intersection. It looks like an N for intersection. Uh-huh.
it's
What about it?
whatever isn't, or whatever isn't in. What I'm confused. Sorry.
No, you're fine. The intersection is the things that are in both.
Things that are in both.
So it's their overlap. That's this region. Like if you were to come in here, this is what I would do. Like if, I mean, so you have your Venn diagram, you have A and you have B. I'm going to go through here and put stuff in. Well, if I'm putting these things in, this is what this looks like. So A union B would be all of this stuff, all of 4 of those elements, but A intersect B is just going to be where they overlap. So it's just that one. So the intersection is an and because it looks like an and, right? The and in logic looks a whole lot like the intersection in set theory, and for good reason. So A intersect B, I read this as in A and B. And I am going to read this one as an A or B. So the and one is a lot more restrictive because it needs to be in both sets. The or one, it can be in either one or both. It can lie in any of those 3 regions for an or statement.
Okay.
But for an and, it needs to be in the very middle. Okay, so the thing here, you have the sets A and B. If A toss B is 1, 5, 7, B toss A is 2, 10. A intersect B is 3, 6, 9. I would like to know what the sets A and B are. So A toss B, if I want to know A, these are the things in A and not in B. So these things are all in A at least. So I have 1, 5, 7, and 8 in A. And B, toss A. This is at my set B with anything that's in A and B removed. So these guys, I will just add in their intersection. Whoa. But now you can see if you were to compute that. So A, toss anything that B shares, we would toss these 3. So A toss B would be these guys. B toss A, if I'm looking at these guys, toss anything that's also in here. That's the 3, 6, 9 again. So I'd be left with 2, 10. But I mean, think about this as you're like on your Venn diagram, right? This region is A toss B. So to pull back in the rest of A, you need the intersection region, which is 3, 6, 9. That would give you all of A. And then this is B toss A, right? Just this like one region. So to get all of B, you're going to need to include the intersection numbers at the 3, 6, and 9. Okay. Do you have any questions about this?
Oh, man.
Okay. All right. The power set is a set of all subsets, and it's got this like script AP. So the power set is a set of subsets. So the elements inside of this set are subsets themselves, which is really weird, and it's a whole bunch of curly braces all together. You need to remember here that the empty set and the set itself are subsets always. Those are called trivial most of the time. But number 1 is done for us. And sorry, these are aligned really weird. If the set is A, the power set is the empty set and the full set. Those are the only 2 ones. Okay. If you have the set A, B though, your power set is the set of all subsets. So the empty set, a subset of this set would be the set containing A and the set containing B. And then you have the set that contains both A and B, which is the full set. So all 4 of those are subsets of this set S. There are 2 elements in the original set. There are 4 elements in the power set. That's how this goes. Oh gosh. You can make a guess about how many would be in the power set of A, B, C, right? Right? It's 8. But the empty set is a subset. The set, all the singleton sets, right? So the set containing A, the set containing B, the set containing C. Those are all subsets, right? Every element in each of those is in the big set. Like if you're looking at it, you know, your question would be, is the set of A contained in the set A, B? Is this a subset of the set A, B, C? Yeah, because everything over here, which is just A, is in this set. Okay, so the singleton ones are, and then all of the like double ones, so A, B, AC, and BC. My curly brace and my comma ran into each other there. And then your set with 3 elements in it. 1, 2, 3, 4, 5, 6, 7, 8. Great. There are 3 elements in the original set, so there are 8 elements in the power set. Or 8 total subsets, or whatever you want to, however you want to say it. Okay, so the thing to be taken here now, this thing is cardinality. We did not talk about that yet. That's the number of things, the number of elements in a set. Whoa. So if S, the cardinality of a set S is n, then the cardinality of the power set is 2 to the n, which is the thing I was doing over here all of those times. So one element in the original set means 2 to the first elements in the power set, 2 elements in the original set. We got 4 elements in the power set, 3, and there are 8, which is 2 cubed. So let's go back and look at some cardinality stuff on the other things. What time is it? 3:11. Okay. I'm going to scroll up if you're good with where we are. Are you?
Yes. Go ahead.
Okay. I'm going to scroll up so we can talk about some cardinality stuff just to get a practice for it. What's the cardinality here of A union B? I'm counting 7. Is that good? 1, 2, 3, 4, 5, 6, 7. The cardinality of A toss B over here is 4. 1, 2, 3, 4. The cardinality of B toss A is 2. The cardinality of A intersect B, 1. We good with all of that or no?
So basically, is it just how many sets are in there? In
It's not
the
how many sets, it's just how many elements are, right?
elements are in a set.
Just
Basically,
count how many elements are in the set. That's the cardinality. Yep,
Okay.
that's it. Where is it that it was something that we actually did that I wanted to talk about. I wanted to use cardinality, but I told myself not to do it yet. Oh, you know, if you were wanting to practice card, huh? What?
Never mind.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's just the number of elements in a set. And then if you wanted to know the like number of things in the power set, that's what these little bars would do. So this is the number of subset is 2 to the 10th there. And this is the number of subsets, which is again the cardinality of power set is 2 squared, so 4. Trying to think about where's that thing we skipped? Oh, there. Yeah, won't have time to do that right now. Okay, I don't have time to do that one. So I think here's what we're saying is that if you had a like proof with sets on your test, it's going to look like, you know, something really straightforward like that or that. But if whatever set stuff is on there will be, you know, different, like this sort of thing or like what we just did. So no, probably no proofs with sets, more like this kind of thing. This kind of thing. And then obviously contradictions, contrapositives, proof by cases. What else have we done in this note packet? Rational numbers, divides. Quotient remainder theorem. Woof. Proof by cases, yeah, I said that. Contradiction, contrapositive, yeah. I think that's, I mean, rational divides, contradiction, contrapositive, that stuff's all good. We skipped a lot of these problems. No, we didn't. Those are fine. Okay, do y'all have any, we have 5 minutes. Do y'all have any other questions you want to ask me before we go today?
I have a question. What is the star symbol? Like, what does it mean? Like when you write proofs?
When I do proof by contradiction and I write this,
Yeah.
that means that I have reached the contradiction. You couldn't hear the sound on this, huh?
Yeah.
The it's like two arrows. Oh gosh, I can't draw two arrows. It's like two arrows running into each other.
Mhm.
So it's to say like this can't be true. We have reached the contradiction. It's like the symbol for that.
Okay, and then we write that when we like reach the contradiction. We just write it
Yep.
next to it. Okay.
Yep. And you don't even have to. Like that's you don't have to. You can leave it off. But yeah, when I did proofs by contradictions in college, my professor had us, instead of drawing boxes at the end of our proofs had lightning bolts at the end instead of boxes. But yeah, the arrow thing, the two arrows running into each other is common because it's like these things are meeting at a head. They can't both be true. And so you've got this sort of like, it's a good place for your reader's eye to go to like, oh, this is where the contradiction happens, kind of a thing.
Okay, thank you.
You're welcome. Other questions or comments as we prepare for the test on Thursday?
I might not be able to do the homework tonight because I have work like right up till 10. And then I also have a test I need to do by the end of the day.
This is the contradiction contrapositive homework or the 6.1 homework or the web assign homework?
Yeah, the web assign homework.
The web assign homework I'm going to move anyway. I'll have that due tomorrow night for anything. I just want y'all to do that before the test on Thursday. I don't care that you do it tonight. So I'll move that. I'll move that. And then y'all are going to do those 5 problems for 6.1. You're just going to hand them in to me on Thursday when you come in for your test. And if you have questions about them before then, obviously you should email me and ask me. I'll be home with my daughter again tomorrow. But if y'all need to meet with me or something in Zoom, you just let me know. She can't go back to school tomorrow. I pray that she can go back on Thursday. Yeah, if y'all need me, just email me and I can set up a Zoom meeting, or I can write out an answer to a question or whatever. But yeah, I'll move the web assign date, so don't worry about those. Don't forget to make note cards for Thursday. Other questions that you have? In my opinion, I have graded everything that I have. If some of you have written homework that you turned in, the copies of that are in my office. And if you want to get those, you let me know and I will get Julia to pull them out of my office for you. So if you have written homework turned in and you would like to see like my notes on that, they are sitting on my desk in my office, so it will not be hard for me to tell Julia where to pull them from to give them to you. Just let me know and I can do that. Okay. Oh, those of you who did turn in your stuff in email form, if you have not noticed, which I'm sure you did because it's pretty irritating for me, so I'm sure it's irritating for you as well. When you submit multiple pictures or multiple PDFs, I can't do them all at one time without downloading them to my computer. Yeah, anyway, I'm not doing that. I'm grading on my iPad. So when you email me a PDF in my email, I can open the PDF, write on it, and send it to you immediately. But if there's separate pictures, I have to do that separately. So that's annoying for me, and I'm sure it's annoying for you to get 4 different emails from me that are my notes on your homework. So if you can do that as a single PDF, that would be good. Your notes app will do that on an iPhone or an app like Genius Scan. You can do batch scanning and submit it that way. Any other questions that you have? No? You're good?
Sounds like it.
Who all is in the classroom right now?
We've got both Logans, Daniel, and Charlotte.
Wow, so appreciated.
And Ruth, right?
Yep.
Okay, Jalen's not in the room.
No, she wasn't gonna be here. She said she needed notes because she wasn't gonna be in class, so
Well, she
I-
won't need notes now because this, you guys, you can see this in Blackboard when you go to click on that Zoom link again. And that, like, you can see the recordings there up at the top. After you click on that Zoom meetings button, up at the top, there's a tab for cloud recordings, and then you can see all the recordings from class. I'm going to continue to download them and put them on YouTube. But in case I haven't done that, when you need them, and if you want to review these, that's where you can go to find them. Sorry about the issue with Teams, but I give up. Okay, y'all, thank you for your flexibility. I appreciate it. I will see you. I will see you all on Thursday, regardless of, because my husband doesn't have class at this time. So I'll be there Thursday. Email me about WebAssign Whitney. I'm going to try to go do that right now, actually. But
I
y'all,
emailed you during class.
okay, perfect. Y'all let me know if you have any questions. I am around. I will be able to help you via email or Zoom, okay?
Thank you. See you Thursday.
All right.
Thank you.
Bye.
Bye.
Bye, y'all.
Thank you. Have a good day.
You too. Bye.